Hello, hello, hello. I hope everyone is doing well. I hope all is good, people. I just wanted to go over a couple of exponential growth and decay problems like we went over in the Hangouts today to make sure everyone understands everything. First of all, exponential growth, okay? Our general formula / model is going to be y equals a times the quantity of 1 plus r to the t power. Now, you might be saying, well, what does all these variables even mean? Okay, so y is going to be your final amount. Okay, once all the time has elapsed, your final amount, once all the time has elapsed. A is your initial amount. And that makes sense because if you look in the formula, a is times whatever 1 plus r is to the t power, right? So a is like what you put in there initially. All right, r stands for rate. So that just, of course, is just going to be your percent as a decimal. Okay, so if it's 50%, 0.50, 75%, 0.75, 30%, 0.30, etc. Okay? And t obviously is, of course, time. All right. Just make sure you look if we're talking about, if you just look at the problem, you can see if they're talking about days, then it's for in days. If they're talking about hours, it's hours, etc. Okay. Now, if you see these formulas are very similar, but what's the difference? Well, for growth, it's 1 plus r. Okay, and the reason being is there, if you think about it as a term of percent, you're saying 100% plus your rate percent, that's 20, so that would be like 120%. It's growing, right? Like, whatever you want to think of, interests, COVID-19 cases. You have a growth right here, okay? It's increasing. And exponential decay is 1 minus r. Well, think of that as like 100% minus r. So exponential decay, like, your car, its value is decreasing. It's decaying right there, right? So you have like 100%, but let's say its decay is 7%. So 100% minus 7%, which is 93%, okay? So it's going down. All right. And there's one other problem I noticed for these word problems that I didn't give you the formula for, but let's just focus on these for right now, and let's go to the actual assignment. Let's see here. Sorry, wrong. There we go. All right. Exponential growth and decay word problem. So we have the formulas right there. Let's take a look at, let's see, we did number 1 and 2 in the Hangout, so maybe let's take a look at number 3. All right. Bacteria can multiply at an alarming rate when each bacteria splits into 2 new cells, thus doubling. Okay, so you're doubling, right? So that tells me, all right, I'm not done reading the problem yet, but I'm just going to write down in my notes, okay, that's going to be growth. All right, I already know because we're doubling, right? If we start with 1 bacteria, which can double every hour, how many bacteria will we have by the end of 1 day? Okay, so we're increasing. So my growth model is, remember, y equals a times 1 plus r to the t power. Okay? All right, so let's see here. Well, we start with only 1 bacteria. A is what we start with, so A is 1. We double every hour. How many bacteria will we have by the end of 1 day? So we double every hour. So what does that mean, doubling? Well, that's 100% increase, right? All right, I have 1, and then if I double, I have 2. That's 100% increase. If I have 2 and then 4, that's 100% increase. So that means my R is going to equal 100%, which of course as a decimal is 1. So my R equals 1, okay? And my time, how much will we have by the end of 1 day? Okay, well, we're talking about hours right here, right? So 1 day, of course, is going to be right here, 24 hours. Okay, so we have it. A is 1, R is 1, and T is 24. And we just use the formula right here, so that's going to be Y equals A, which is 1, times 1 plus R, which is also 1, to the T power, which is 24. All right, and then just go ahead and simplify. Y equals 1. 1 plus 1 is 2 to the 24th power, okay? So that's going to be 1 times 2 to the 24th power, okay? Careful, in this case it wouldn't matter, right, because it's just 1, but remember, follow PEMDAS, you want to do your exponent first and then do the multiplication. I am, of course, right here doing, I'm going to be doing this on the calculator anyway, and the calculator does order of operations. So I'll just go here, okay? So I have right here 1 times 2 to the 24th power, right? In this case, I didn't have to put 1 there, right, because it's just going to be itself, but let's just follow it. 1 parentheses 2 to the 24th power, enter, and there we have it. So it looks like we have right here 16,777,216. All right, so 16,777,216 is my final answer, and I'm sticking with it. All right, there it is. All right, all good. So that's how many bacteria we'll have within 1 day. All right, it's a huge increase, but, you know, that's what happens with bacteria. Okay. Let's take a look at another one. Let's see if we can look at maybe a, let's look at 5. That's a little bit different. The population in Winnemucca, Nevada can be modeled by P equals 6191 times 1 plus 0.04 T, where T is the number of years since 1990. What was the population in 1990? By what percent did the population increase by year? All right, so this is a little bit more conceptual, isn't it? Okay, so let's see here. So it's going to be modeled by P equals 6191, all right, times 1.04 to the T power. Okay, so let's answer the first question. Let's call that A right here. What was the population in 1990? Well, it says right here that T is the number of years since 1990. Okay, no problem. Well, so the population in 1990, that would mean that right here, in 1990, T equals 0, right? 0 years since 1990. So we'll go just plug that in. So that's going to be P equals 6191 times 1.04 to the 0 power, okay? And of course, what is anything to the 0 power, right? Anything to the 0 power right here, of course, is going to be 1, all right? So that's going to be P equals 6191 times 1, or something to the 0 power, you can just go shunk, cross it out, right? Because it's just 1, it won't affect the problem. So in this case, for part A right here, the population in 1990, all right, is 6,191, okay? Very good. All right, let's take a look at part B. By what percent did the population increase by year? Okay, well, if we go way up here, right, I have my growth model right there. So let's go and just recopy that right here. So this is growth, right? Obviously it's increase, all right? So my growth model is y equals a times 1 plus r to the t power, right? It's plus. Don't get confused by plus and t. T I'm writing as cursive, right? All right, so no problem. So I'm going to compare that to what we had right here. We had P equals 6191 times 1.04 to the t power, okay? Now, you can see right here, if we had compared it to the original, we could have also said, well, I said A is the initial amount. The initial amount is 6191. That was what we had in 1990. So you could have thought of it that way, right? 1 plus R. and we get 1.04. So we're thinking about this right here as 1 plus r equals 1.04. Well, wait a second. That just means that r equals 0.04, right? 1 plus 0.04. So right here, that means my rate equals 0.04, okay? By what percent did the population increase each year? So what we're doing now is we're putting the decimal back to a percent, right? So we're going to say right here that is going to end up being 0.04. If we go move to the right, that is 4%, okay? That's it. So part B is just going to be 4%, okay? That was a little bit more difficult, but not impossible. Let's see here. Oh yeah, number 9. Just wanted to show that right here. Actually, let's do a decay and then let's do number 9 right here. So number 8, let's do first. An adult takes 400 milligrams of ibuprofen. Each hour, the amount of ibuprofen in the person's system decreases by 29%, right? So how much ibuprofen is left after 6 hours? So this is going to be right here a exponential decay model. Or formula, model, formula, whatever word you want to use, right? All right, so no problem right here. So let's do it. So that's going to be y equals a times 1 minus r to the t power. All right, once again, a is the initial amount. Sorry about that, initial amount. Okay, a is the initial amount. Sorry, it's a little slow. R is my rate. And like I said before, T is time. Okay? Y is obviously your final. All right, so my initial right here, my A is going to be 400. All right? Each hour, the amount of ibuprofen in the person's system decreases by 20%. So my rate is just going to be 29% as a decimal, which is 0.29, right? Just go ahead and move that 2 to the right. To the left, I'm sorry. And then finally, T is the number of hours. How much is left after 6 hours? Because it's right here. Each hour, it decreases by 29%. So we're talking about hours. So that's going to be 6 right there. We'll just fill this out. Y equals A, which is 400, times 1 minus R, which is 0.29, to the 6th power, right? Okay, so we're subtracting right here. Let's see if I can get more room to write here. So that's going to give me y equals 400, and 1 minus 0.29 is going to be 0.71 to the 6th power. All right, all good there. So we're just going to use our calculator. We'll just go and say right here, this calculator does order of operations. Most scientific calculators do as well. All right, it doesn't necessarily have to be a graphing calculator. So we'll say 400, parentheses, 0.71, close parentheses, and then right here we're going to say to the 6th power. Very good. So we get 51.24. Now it says how much ibuprofen is left after 6 hours. Okay. So, I mean, I would really accept, you could say 51.24 ibuprofen, because you could split an ibuprofen pill. But if you want to just round off like approximately 51 pills, you could say right here is a better way of maybe saying this. So I'm just going to go and say approximately, just round 51 pills, okay, is left in your body after 6 hours, okay? So approximately 51 pills are in your body after 6 hours. Okay, good enough right there. And then lastly, these ones might have been a little bit confusing because I did not give you the formula for compound interest. All right, so this is a little bit of a different formula. All right, if you're doing compound interest, not that much different though. So these are compound interest is going to be obviously growth. Interest, you're gaining money, right? The difference right here is these formulas are going to be y equals a, parentheses, 1 plus r over n to the nt power, okay? So defining this right here, once again, y is your final amount. A is your initial. R is going to be your rate, once again. What is n? N is the times you're compounding it. Number of compoundings. Okay? And T is, once again, time. Okay. So right here, the account pays for 2.5% annual interest compounded monthly, okay? Every month it compounds the interest, okay? So no problem. But it's 2.5% annual interest, okay? So let's take a look right here. All right, so that's going to be right here. We'll say right here, y equals, once again, a, parentheses, 1 plus r over n to the nt power. Okay, so A is $1,600 in the bank account. R is going to be 2.5% as a decimal. Okay, so that means I'm just going to go move that 2 to the left as 0.025. Your N is your times compounded. Well, this says compounded monthly. There is 12 months in annual means 1 year, so that's going to be 12, n equals 12. And your time, of course, is right here. You find the balance after 3 years, right? So T is 3. Okay, so we can all fill this out now. So we'll say y equals A is 1,600 times 1 plus R, which is 0.025 over n, which is 12 to the nt power. So n is 12 and t is 3. So to the 12 times 3 power. Okay? That looks like 12.3. It's actually 12 times 3. So let me put that in parentheses. 12 times 3 power, right? Okay, so what is that? That's going to be 1,600 times 1 plus 0.025 over 12 to the 12 times 3 is 36 power. Now you can actually do this if you have a good enough scientific calculator, even a cheap scientific calculator. You can just do this all at once right here. It might be easier. So watch how I do it. I'm going to say right here, 1,600 parentheses. Then I'm going to say right here, 1 plus 0.025. Now, these calculators do order of operations, right? So you can just go and put divided by 12, and it will do the division first and then add, and then you just close the parenthesis up, though. And then that's going to be to the 36 power. So you can do it all at once like this. That's fine. That's going to be 1724.48. All right, so my answer is going to be right here. $1,724.48 rounded to the nearest cent, right? Rounded to 2 decimals, that's it, okay? So part B, compounded quarterly, in this case, right, you use the same values, except for R is 1.75 in this case, so R would be 0.0175. And your compounded quarterly, that means N is going to equal 4 times. All right, and C, annual interest compounded yearly. Well, wait a second here. If it's compounded yearly, that means N equals 1, which means, guess what? Just go back to your regular growth formula, because if N is 1, let's look at this formula. If N is 1, that means R over 1 times 1 to the 1 times T, right? So it's not going to affect actually your formula at all. So you could just go back to your regular exponential growth formula for this one, right? If it's just compounding 1 time per year. All right, guys, I hope this gives you some to go on, and we can go over, this is like a lot of problems on this worksheet, but we can go over more of it later, but this will give you some, and I think we're good for right now. Remember, if you have any questions, just contact me through email or Google Classroom, okay? And I hope everyone's in good health. Have a great day. See you later.